Welcome back. In the previous lesson, we looked at what a CPU and a microprocessor was, and in this lesson, we're going to understand the purpose of the various components inside the CPU. We're going to do a deeper dive into the CPU itself, and we're going to look at a way of structuring components, which is known as the von Neumann architecture, and study that in a bit more depth. Hopefully, by the end of this particular lesson, you'll be able to describe the process of the fetch, decode, execute cycle, sometimes called the FDE cycle or the FE cycle, including the role of each of those components in that particular process. The CPU is one of the fundamental parts of a computer. How is that CPU actually made? What's inside that particular CPU? Most people never get to look inside it. Most people will just simply have a look at the processor, or often not even that. So let's start by looking at how a CPU processes our instructions. Now, normally what happens is that the CPU and its components operate a queue system where all the instructions are particularly stored. So whenever you run a program, it is a sequence of instructions, and these instructions are stored in a queue system. The CPU then fetches them one by one, as it can only process one instruction at a time. It decodes that particular instruction according to a pre-stored instruction set. It then executes it, and the process repeats itself. Now, it has a number of parts that help it with this particular process, because remember, there is no human brain inside a CPU. It's just a bunch of logic gates and flip-flops and circuits and transistors and capacitors. Everything is electronic. So how do we get it to understand our instructions and execute them? There's a lot of parts that help with that particular process. As far as you're concerned, a central processing unit consists of a control unit, an arithmetic and logic unit, registers, and buses. These are the main parts of a CPU. There's a diagram on screen which you will need to memorize so you understand how these parts are arranged. Pause the video and spend some time looking at it, but we're going to go through this diagram and the components in a bit more depth in this lesson. Let's start first of all by looking at the von Neumann architecture and a brief trip down the history of computer science. Now, early computers were fed data while machines were actually running. It wasn't possible to store programs or data anywhere. There was no particular RAM or hard drive, which meant that they couldn't operate without human intervention. And the first programs had to be entered using punch cards. So the program itself was on these punch cards. The data which we were going to input into the program had to be entered by manipulating dials and valves. Now, as you can see, computers were very complex machinery, and not everybody could use them. And often multiple people, multiple expert people had to be involved in operating a computer. In the mid-1940s, John von Neumann developed the concept of the stored program computer, which has been the basis of computer architecture ever since. Now, the stored program concept basically meant that the computer memory could store programs as well as data. So it wasn't the punch cards or the data, it was both of them together. Now, these stored programs were made up of instructions which could then be executed in a sequential order, one after the other. It also introduced the concept of a CPU, and the CPU was able to access the memory directly instead of via a human, so there was no human being involved. And that was quite amazing for that particular time. The architecture that he came across in a very basic form is on screen. You'll need to learn to draw this from memory, because in an exam, either you'll be asked to draw it at some point or talk about it. So if you can visualize this diagram, it will make life a lot easier for you in the exam. So do pause the video and have a deep look and maybe perhaps draw it out before continuing. An architecture is basically a design of a computer system which includes the components it contains. So we're going to start with the first component that's part of this architecture, which is called the control unit. So a control unit is the component that controls the entire fetch, decode, execute cycle. It reads an instruction from memory. The address of this particular location where the next instruction can be found is stored in the program counter. This instruction is then interpreted using the fetch, decode, execute cycle. During that particular process, signals are generated along the control bus to tell all the other components in the computer system what to do. So the control unit ensures synchronization of data flow and program instructions throughout the computer itself. It's a very important component. The next component that aids it is a system clock. And this is used to produce timing signals on the control bus to ensure there's vital synchronization that's taking place. Without the clock, the computer would simply crash because it won't be synced. It might try to save the data and fetch the instruction at different times, and that could cause a conflict. The greater the clock speed, the more instructions the CPU can process per second. This is currently measured in gigahertz. So if you've got a 6.2 gigahertz processor, which is the current desktop benchmark, That means it can process 6.2 billion instructions per second. The next big component is the arithmetic and logic unit, and this is the maths part of the CPU. The ALU allows the required maths to happen, the required arithmetic, so addition, subtraction, shifting, or logic operations, and or not, those kind of things. It is possible for a computer to have more than one ALU to carry out specific functions. So you could have a control unit and multiple arithmetic and logic units to do various different kinds of maths. Multiplication and division are carried out by a sequence of addition, subtraction, and left or right logical shift operations. And we already know this from Unit 1. The next important component you need to know about is the immediate access store. This is basically another name for RAM. Now, RAM can be directly accessed by the CPU. It's known as primary storage. However, it is not part of the CPU and it just resides outside the CPU. So the CPU takes data and programs held in the backing storage or the secondary storage, for example, a hard disk drive, and puts them into RAM temporarily so it can work with that particular data before saving it back to the hard disk drive. Now, this is done because read and write operations carried out using RAM are considerably faster than read and write operations to a secondary store like a hard disk drive. Important data needed by an application will be stored temporarily in RAM to considerably speed up that particular set of operations. If you had to access the hard drive all the time, a computer would always be very slow. Now, to help the CPU access this data from RAM, there are a number of registers that are built into the CPU itself, and registers are small storage areas, special memory units, which are just used by the CPU. They store really important data, address instructions, which might be needed by a current process a CPU is dealing with. Registers can be general or special purpose, and we're only going to deal with the special purpose registers for this particular syllabus. So what are these registers? Well, you've got this current instruction register, also known as CIR. You can write either one in the exam. Accumulator, ACC. A memory address register, MAR. A memory data register, that's MDR. And a program counter, which is also known as PC. Now, no, the PC isn't named after this particular register. In addition to these registers, there are various system buses, three in particular, which are used to connect the CPU to the memory and to other input and output devices. And these buses are used to transfer data and signals between the CPU, memory, and other devices. So there's a control bus that allows the CPU to connect to input and output devices, RAM, and the various different ports. There's an address bus, which allows it to connect to the various different devices and the memory. And then there's the data bus that also allows it to connect to the memory and the various different input and output devices. If a CPU wants to do a read operation from RAM, it will send a signal down the control bus, and then it will send the address of the location it wants to read on the address bus, and the data itself will be transferred from the memory using the data bus. So all three buses often operate in tandem in synchronization to make the computer do what it needs to do. So these system buses are used as parallel transmission components, and each wire in the bus transmits one bit of data. Now you need to make sure you know the purpose and names of all three buses. Let's start with the address bus. The address bus carries addresses throughout the computer system. That's between the CPU and the memory or other devices. The address bus is unidirectional, which means that the bits can travel in one direction only. This prevents addresses being carried back to the CPU, which could be a very undesirable feature because that means you're giving control away to a device or RAM. Now, the width of this bus is very important because the wider this bus, the more memory locations that can be directly addressed at any given time. So, for example, if you've got a 2-bit bus, that means 2 to the power of 2 is 4 address locations can be addressed by the CPU. A 16-bit one can address 2 to the power of 16, which is 65,536 memory locations. And if you've got a bus width of 32 bits, that allows almost 4 billion plus memory locations to be simultaneously addressed. So a 32-bit CPU can address a max of 4 GB of RAM as a result. And often people sell you more RAM than that's necessary. Data bus, on the other hand, is a bidirectional bus, which means it allows data to be sent in both directions. Now, this means data can be carried from the CPU to a location and vice versa. It's important for you to point out that data can be an address, an instruction, or a numerical value. So we just don't mean addresses all the time. It could be a command, it could be data that has to be executed by that command, anything. As with the address bus, the width of the data bus is also important because the wider the bus, the larger the word length that can be transported. Now, what's a word length? A word length is a group of bits which can be regarded as a single unit. So a 16-bit data bus, the word length is 16-bit. A 64-bit data bus has a word length of 64 bits. So the larger word lengths can improve the computer's overall performance. But again, be aware that if you've got a 32-bit CPU and a 16-bit word length, you've got a bit of a bottleneck there. And if you've got a larger word length, like a 64-bit word length, the CPU can't access that. It'll only be able to access 32 bits at a time. The final bus we're going to look at is called the control bus. The control bus is also bidirectional, and it carries signals from the control unit to all the other components and vice versa. It's normally about 8 bits wide, and there's no real need for it to be any wider since it only carries control signals. So 2 to the power of 8 means we can send up to 256 different commands, which can be things like read, write, delete, switch off, and so on. So how would a typical memory read operation work? Well, the computer memory is made up of a number of different partitions, and each partition is given an address, and each address will hold some content, which could be data, a command, or another address. So this address will uniquely identify a location in the memory, and the contents will be binary values stored in each location because the computer deals with binary. So let's look at an example. On screen, you can see some addresses and their contents. We want to read the contents of memory address location 11110001. So what happens is that the rest of the location to be read is first written into the MAR. It's normally in the PC, then it's written to the MAR. A read signal at the same time is sent to the computer's memory, so it knows what to do at that particular address that it's going to get from the MAR. So the contents of the memory location 11110001 are then put into the MDR, and that's then transferred to the control unit via the CIR. Now, a memory write operation works the same way. To write a value, the process is basically reversed. Let's write the value 10010101 into memory location 11111101. So data is first stored in the MDR. This data has to be written to the location, and this address is now written into the MAR. And a write signal is now sent via the control bus to the memory. So the memory will take the data from the MDR and writes over the previous data in the correct memory location. Okay, that's enough about memory. Of course, there are also input and output devices in the computer system, and these are also outside the CPU. And we're going to be looking at all of these a bit later on. However, all you need to know for now are that they're the main method of entering data into and getting data out of computer systems. So input devices convert external data into a form the computer can understand and can then process it. And input devices typically are keyboards, touchscreens, microphones. Output devices show the results of a computer processing in a human understandable form, and these include printers, monitors, and loudspeakers. The CPU controls all of them using the control bus. Okay, let's leave all of those components there. Let's focus on the fetch, decode, execute cycle. Now, the CPU has to process data and instructions through the use of those input devices. Now, when data and instructions are input, they're stored in RAM. If the user wants to open a file, for example, that's on the hard drive, this data will have to be brought from the hard drive into the RAM. So in order for data and instructions to be processed, they need to be brought from the RAM into the CPU. And this happens at the fetch stage of this particular cycle. So to carry out a set of instructions, the CPU first of all fetches some data and then stores them in suitable registers. Both the address bus and data bus are used in this process to transmit data, addresses, and the control bus is used for signals. Once this is done, each instruction needs to be decoded by the CPU before finally being executed by the ALU and CU combination. This whole process is known as the fetch, decode, execute cycle. Now you can see a flowchart on screen, so my suggestion is pause the video and have a look at that in a bit more depth. We're going to look at this particular flowchart in word form in a moment. Okay, so what happens in the fetch stage? A component within CPU called the program counter stores the next address. And this component is an example of a register. The details of this address will be a location within RAM. So both data and instruction can be stored in another register, which is called the memory data register. We'll get to that in a minute. So think about it this way. The PC stores the next address, and this address is then copied into another component called the memory address register. Now this address is transported from the PC to the MAR using the address bus. Now once the MAR has received the address, it now knows where to find the instructions in RAM, and then a signal is sent via the control bus whether we want to read or write to this particular address. To retrieve the instruction, the MAR needs to send the address to the location in RAM, and it again uses the address bus to do that. So whenever we're using addresses between the PC, MAR, or the RAM, we use an address bus. Once the address is received at the location in RAM, data stored in the location or any instructions are copied into the MDR, and we use the data bus for that. So when the MDR has received the instruction, it sends this to the current instruction register, and it also uses the data bus for that. So just remember that when we're transferring addresses between the PC, MAR, and the RAM, we use the address bus. And when we're transferring data from the RAM to the MDR and then to the CIR, we're using the data bus. Now, the CIR is part of a component within the CPU called the control unit, and it is the control unit that's responsible for the next stage of the cycle, which is the decode stage. What happens is that the instruction is received and the control unit then decodes the instruction. So it does that by comparing it to an instruction set. And this is a set of commands that are understood and can be processed by the CPU. And these commands are in machine code. So once the instruction is decoded using the instruction set, it can now be executed. So we move on to the final stage of the cycle. Now here, any actions that are required for the instruction are carried out, and it will probably involve some kind of mathematical and logical calculation. In this case, the arithmetic and logic unit comes into play along with a special register, which is called the accumulator. Now this accumulator stores the interim or the middle values of any calculation, because calculations can have multiple steps. So sometimes that data is stored in the accumulator while it is being processed. In addition to that, sometimes the CPU needs to send control signals to appropriate components, perhaps to display outputs, and just to complete the instruction in a logical manner. And that all happens in the execute stage. So please make sure you're familiar with how the process works, and hopefully you should be able to answer the following questions. You should be able to describe the function of the three buses using the von Neumann architecture. You should be able to explain the stages of the fetch, decode, execute cycle. You should be able to describe how bus width and clock speed can affect computer performance. You should be able to draw the diagram for the von Neumann architecture. And you should be able to state the role of registers such as PC, MAR, MDR, CIR, and the accumulator in the fetch, decode, and execute cycle. Now, this was a very long lesson, so you should probably go over it a couple of times to make sure you understand all aspects of it. If you do have any questions, please do get back to me. Otherwise, I'll see you in the next one.